This is the temporal and numeric planning track, second part. Welcome. We have 4 talks, 20 minutes slots, including questions. And so we can start with the first talk by Ángel. Please.
Thank you. So thank you for being here. My name is Ángel Aso-Mollar. I'm going to present you my work, a sampling approach to planning with infinite domain control variables, which was made alongside the Aineto, Enrico, Scala, and the Onaindia. Okay. So just to briefly introduce the problem, we have this numeric planning problem. Okay, we have a drone that wants to take some pictures of trees, right? So we define the numeric planning problem by addressing the propositional state variables, which can be that to take pictures of trees, okay? Then we have the numeric state variables that define the position of the drone and the trees. Then we have the actions of the problem that actually model the transitions between the states of the problem, right? And some initial configuration and certain goal conditions, in this case that both trees have been taken a picture, okay? So how do we actually get to a goal state in numeric planning? So we search, and in planning in general, so we search over the space of all possible configurations of the problem, attending to the dynamics of the problem, okay? The search is usually performed by branching over the set of all applicable actions of the problem, which is usually finite and discrete, okay? So if we are in this configuration, the drone can only move left, move right, and down, okay? But the challenge here is, well, imagine that you actually wanted the drone to move freely over the state space, right? Over the geometrical space, sorry. Okay, so you want free XY movement of the drone. How can you do that? Well, we have proposed a framework that is called control variables that are free numeric variables that allows us to define actions with numeric parameters. This concept is completely semantically equivalent to the notion of control parameters in the literature. And yeah, here we have an example of this. So we have a drone here and the same drone as before, and we have an action example that could be that the drone moves k units to the right, where k can be a number between 0 and 9, for example, okay? We can represent this compactly with this tuple. This is the identifier of the action, and this could be a valuation of the number. So for instance, we could describe here move right 5.25, okay? What does these variables represent? So they often represent physical quantities that to make actions have some desired effects. In this case, we have movement, but we can also describe amounts of production, money withdrawal, etc. Okay, a lot of things. And they are just lifted numbers in a sense, right? You can define them with a domain, with a numeric domain, and this domain can be infinite or finite if desired, okay? So how does this look like in the formalization? So we only need to add a new set, which is the set of control variables. And then for every action of the domain, for instance, here we have the move right action of the drone, which needs beforehand to be, we need to define beforehand how much we want the drone to move in numeric planning. So when considering this control variable, we can define variable increments in this sense, right? This is very important, this note here. Delta is not part of the state, but of the decision. So the planner actually has to commit to a value of delta when making a decision, okay? This yields an infinite and structured decision space, okay? Why? Here you have, for instance, the action move right, and then for every possible valuation of this number that can be between 0 and 9, we have a successor state, right? This happens for the action move right, move down, but we could also have actions that do not use control variables, okay? For instance, the actions for taking the pictures of the trees are discrete, okay? So by defining these, plans in this setting are no longer sequences of actions, but of pairs action valuation, okay? So here we have a plan for this setting. in which we say that the drone moves to the right certain amount, then moves down, takes a picture of the first tree, then moves down again, left, and takes the picture for the other tree. Okay. So how do actually planners handle this in the literature? So they usually represent these numeric decisions as constraints rather than as explicit decision points of the search, right? This concept of numeric parameters was firstly introduced in the planner TMLP-SAT, which is a constraint satisfaction planner. And then this idea was further formalized in the Popcorn planner with the concept of control parameters. And Popcorn performs a hybrid search combining pop search and constraint optimization, constraint satisfaction, sorry. Okay. This idea was later inherited by the NextPath planner, which is currently the only planner capable, as far as I know, capable of handling this type of problems. Okay. This is very costly due to the reliance on a separate solver. So we see a snapshot of the Popcorn planner, of the Popcorn paper, sorry. And here we can see that we have a finite set of action choices, but then the infinite nature of this state space, right, arises from the use of numbers in actions, but this is left to the constraint space, right? So here we have this natural evaluation of a pure constraint approach to a hybrid search and constraint approach. And then the challenge here is if we can systematically explore this infinite unstructured decision space without relying on anything else, just by pure search. Okay, this is what we actually try to do here. So for this, we introduced the delayed partial expansion framework, okay, which is inspired on regular forward search scheme, in which we have some node evaluation criterion, as we already know, and then the next selected node is the one with the lowest or the best neg value, okay? So in this type of schemes, we already know that when we select a node, we expand it and we generate all of the successors of the state, right? But in this case, we have an infinite amount of successors. So we cannot generate all of the successors since we cannot store in memory an infinite amount of nodes, right? So what we do instead of generating all successors is we use a sampling function to iteratively generate subsets of successors each time, right? So, well, since we are partially expanding nodes, okay, since we are partially expanding those successors, we cannot close nothing, okay? Everything remains open at all times in principle, okay? So here we have an example. We use a sampling function. In this case, we are just sampling one successor each time. And yeah, the next selected node is the one with the best neg until reaching a solution, okay? This approach is nice, but it needs some more adjustments because of this problem. So I want to illustrate this with an example, right? The problem of blocking parents. So imagine that you have a node, okay, with a neg value, and that node gets selected, okay? But this node has infinitely many successors, but every successor has a worse neg value than the parent, okay? What would happen here is that we try to sample successors indefinitely, but since the parent has a better neg value than all of the infinitely many successors, the parent would always be the first in priority, right, in the search. So what do we do here? We need some mechanism that prioritizes newer expansions. Okay, this mechanism is what we define as rectification functions. A rectification function is nothing more than a function that modifies a node's neg value with every partial expansion that has already been performed in that state, okay? So as we can see here, each time a successor is generated, the parent's neg value is slightly increased, okay? And well, eventually, this is the same example as before. Eventually here, other nodes take priority, right? As we can see here. These two mechanisms, both using a sampling function to iteratively generate subsets of successors, and this rectification function leads us to our full algorithm, SBFS, in the ICAPS paper for now DPEX. Okay, we changed the name. And yeah, it's a regular forward search algorithm that samples new successors for the selected node instead of generating all of the successors, and then stores the sampled successors and the parent with the value rectified. Okay? So yeah, this algorithm has some interesting theoretical properties that were further analyzed in an ICAPS paper published this year. And well, if we restrict ourselves to some sampling and rectification functions that have desired properties, okay, then we can prove that the algorithm is actually probabilistically complete. This means that the algorithm will find a solution if one exists with probability 1, when the iterations of the algorithm tend to infinity, okay? And some other properties about the quality of the nodes. So, just to wrap up some experimental results, we actually performed 2 different sets of experiments in this paper. We analyzed domains from the control parameters framework, the cache point domain, terraria, and procurement, which were introduced in the popcorn planner or paper. And then other sets of experiments that actually analyze usual numeric planning domains from the IPC, from the numeric IPC, but with a twist. So what we did here was to actually enable variable applications of the same action as in rolling, if you are familiar with rolling, or up to jumping actions, unrolling, etc. This is the idea, okay? We use this to decide the number of repetitions of the action. And yeah, the approach performed very competitively against baselines. Here we have that for the next flap planner, the coverage, the difference in coverage is very high. This is probably because NextFlap heavily relies on a solver for actually committing to these numeric parameters, okay? And then we perform these experiments of rolling with respect to the numeric parameters, and for this we use 2 heuristics with a usual GBFS scheme with the ENHSP planner, both with the multi-repetition relaxed plan heuristic with up to jumping actions, and with the goal counting heuristic, okay? We can also see that our approach solves problems. These problems actually are several orders of magnitude harder than the ones that the baseline solves. So for instance, in the terraria domain, the difference is very high. Also in the block grouping, we solve instances up to 200 blocks, okay? The drone also 200 locations. Anyway, this works competitive against this. And yeah, there is a lot of different directions for future work, a lot to do here. So there are these orthogonal directions of work. We have we need some work on heuristics definitions, because when introducing numbers into the decisions, then the usual heuristics don't work anymore, right? And for this reason, well, we are currently investigating some new mechanisms, and we also want to investigate other sampling techniques, more efficient sampling techniques, because currently we are only using uniform and other techniques, but we need to further investigate in this, and also for the rectification functions. Okay, so a lot of work, and then these are not independent, so they can also interact with each other. We can also use the heuristic both for sampling and rectification. And yes, this is everything. Here you have a planner, which we recently did. That is a GitHub. You can download it and you can test it for your domains. The domains doesn't need to be with control parameters. You can actually just apply DPEX for any problem you want, okay? It will work better, I think, for this type of problems, but it could also work for problems with very high branching factors or whatever. Okay, so yeah, thank you very much.
Can your problem be formulated as a mixed integer program? You have continuous variables also, so is that something you have explored?
Can you repeat? I don't.
Have you formulated your problem as a mixed integer program?
No, no, we haven't. No, that's interesting. Yeah, but we haven't.
How do you make sure that when you jump, you don't break a precondition?
No, you're completely right. So we actually assume that the domains are convex, right? So you cannot have, that's another line of work. You cannot have an obstacle here because this would just ignore that there is an obstacle, right? So the domains that in which we tested this are actually convex, right? You have no obstacles in between.
So you said that the prior approaches failed to solve these problems. Was that an issue of they timed out, or they ran out of memory?
We actually think it's a matter of, yeah, I think time. Because we ran this for 1 hour, I think, for it. This was made a long time ago, so I don't really. But I think it was 1 hour. And yeah, the DPEX did it like in 3 seconds.
Did you compare the memory footprints? Because it seems like if you have this tree that you're never closing any nodes, that you...
Yeah, that's a problem, right? That's a problem. We actually, there was a 8 gigabytes memory limit, and sometimes DPEX out, yeah. Not usually, but sometimes it happens. It also has to do with the heuristic function, right? Because if you have a good heuristic function, then you are more, like the direction is more clear. The problem is that we don't have good heuristic functions. We could only use heuristic functions that are independent of the transition system, such as, well, blind heuristics or goal counting heuristics, numerical counting, etc.
But if I can add something, so this is definitely a limit of all these state space search approaches. Yeah? Eventually you're gonna run out of memory, okay? So you cannot let it run forever, because as you are saying, you need to store the nodes somewhere. And, yeah.
I was curious about how you handle the sampling, in the sense that I imagine that I can sort of trick, or let's say, make a planner explode by creating a domain in which you have to guess exactly one number, right?
No, that situation cannot happen in this sense, because since you have let's say a continuous decision space, right? Even though it's not continuous, but it's dense on the continuous. But yeah, equality constraints are not meaningful in this setting. Because you cannot sample with an infinite precision, with infinite decimals, the probability of sampling a number.
Even on integers, right? So if you have to go exactly in that cell, so you have to guess exactly 15 as a number, but in my modeling, I like to choose an integer number, right? The probability of picking that one is very small.
Yeah.
Would that be like your the worst possible case for your plan?
Yes.
And did you observe any situation like that in your experiment?
Yes. In fact, in the sailing domain, like you have this unbounded. Are you familiar with the sailing domain? So you have this unbounded seek, and you can basically move wherever you want. But here you have to sample the safe person action here. So if that action is not sampled, maybe the boat goes there and it will never get, right?
Right.
So for that, what we actually are trying to do is to augment the number of samples of the algorithm, right? So that there is a higher probability of sampling that particular action.
But are you biasing it somehow towards smallish numbers? Because I was thinking exactly the same, like, I don't know, I guess 3,000, right? And then I have to sort of say back.
Yeah. No. the bias is basically the heuristic function, right? If that heuristic function is good, then this would be worse than this. But since the heuristics are basically stupid, then it doesn't matter, right?
Okay, that's a quick question.
But in the realistic domain, you do have some properties, like some continuous function properties of the plane of this that you can exploit. So did you try to integrate any of these properties into your...
No, that's actually a line of work, yeah. Yeah, this is very blind, but it works quite well. So yeah, this is a very promising line of work. Yeah. Thank you very much.
Thank you again.
Thank you.